Electricity is one of the most important engineering inventions we sometimes take for granted. It powers our current lives. Every day we turn on lights, turn on our computers, charge our cell phones, and charge our tablets. In our day-to-day lives, it seems like there's always something to plug into the electrical outlet on the wall. Our lives seem to deem constant electricity from the electrical power grid. But where does the electricity come from, and what is the electrical power grid? The electrical power grid is just a large and complex network of transformers and wires. Power plants and generators constantly supply and feed electricity into the grid, which is then transmitted through a series of wires and transformers to where they are needed, the consumers. Thomas Edison, the founder of General Electric, or GE for short, created the first practical power grid that could power entire neighborhoods in 1876. Today, General Electric, a large international company, composed of many divisions, including GE Power. Within the power division, they manufacture large, air-derivative gas turbine generators that bring power to residents all over the world. But what happens when one of these generators shuts down? This is where the Remote Monitoring and Diagnostics team comes into play, or also known as RM&D. The RM&D division monitors over 480 units turbine generators from around the world, with 40 of these gas turbine generators being on their new pilot process. For this project, we'll be looking at what happens when a gas turbine generator monitored by the RM&D team shuts down or trips. We will focus on how a team of hard-working engineers use the pilot program to diagnose, prescribe, and get the generator back online as quickly as possible. Our goal is to address the trip and get back to the consumer within a detailed diagnostics and prescription about how to get the generator back online within 30 minutes.
Now, let's begin by explaining what the pilot process is comprised of. Many companies around the world use gas turbine generators to convert mechanical energy to electrical power. Okay, our pilot process begins when there's a failure or trip in one of these gas turbine generators. When a trip occurs, the local on-site monitoring unit, also called the OSM, found on the generator, takes note of the trip and triggers a flag, which is later attached to an email notification. The OSM sends an immediate trip notification out through a server-to-server connection to the RMD center at GE. The RMD team receives an email with this notification and begins to validate if an actual trip has occurred. The validation step uses different tools such as ODV, Optimal Data Viewer, DPS, Distributed Power Service Portal, and Excel to make sure the trip was an actual engine failure. During this step, customer and generator information is also gathered. The real hard work of the pilot process begins if an actual trip occurred. At this point, the RMD member validating the trip sends out a notification to various team members. The team is comprised of someone from the RMD division, someone from the PSE, a product service engineer, and someone from the QRC, a quick response center member. These team members gather in a conference room and use their expertise to quickly diagnose the problem. There, they use gathered data such as the first out code, the per second data, the trend graphs, and the historical data from the tripped gas turbine generator to analyze where, when, why, and how the trip occurred. Once we know why the gas turbine generator has tripped, the team will call the customer with a prescriptive recommendation on how to fix the generator. If at any time the timer hits 30 minutes, anywhere during the process, an RMD representative will make sure to call the customer to either tell them how to fix the problem on the generator or update them on the status of the analysis. Now, let's look at what we got in our Simium model when we represented the pilot process time studies in a simulation.
A simulation was chosen to represent the process due to its ability to accurately model the variability of GE's process, as well as its ability to model what a change in the process would result in without making the investment to apply it to the actual system. Due to a lack of available data, our team had to adapt and model the process in a different way. We went out and collected 3-point time estimates from the appropriate personnel at GE Power. With these estimates, we were able to then model the processes with a higher degree of confidence and could establish a baseline in which to compare our modified process. GE sent our team a file that contained all of the recorded Control Action Advisories, CAAs, for the past several years. All of the CAAs had a timestamp that was associated with each time the advisory occurred. The team performed a statistical analysis on the data to discover the time in between occurrences. We could then input the data into the statistical analysis software Minitab to find the appropriate distribution that best fit the data. Again, it is important to note that our model is based on a series of assumptions, and as a consequence, so are the results. Additional data needs to be collected in order to obtain more reliable distributions and time ranges. Without this data, the best that we can do is model the process based on a series of assumptions. After we ran our simulation on the original pilot process, we established that the mean time to complete a detailed analysis for a CAA was approximately 73 minutes. One of the main drivers of this large time was the time variation that it took for RM&D to see and react to the email notification that they received from the OSM. After researching, we discovered that if there was a blast-style notification that could be seen by RM&D, they could react in approximately 34 seconds. With this implementation, we were able to reduce the average processing time to approximately 48 minutes. But even more outstanding, it increased the amount of saves from about 2 to 39, resulting in an increase of $5.5 million saved. From this, we devoted our attention to the next time driver, which were the CAA validation and data gathering steps. To improve these steps, we recommend reprogramming the OSM to provide the information that drives these higher times. Valuable time is lost searching for information needed to validate the trip and perform the prescriptive analysis. If this information were to be provided from the original notification, we predict that it will reduce the average time to roughly 37.5 minutes and increase the amount of saves generated from 39 to 101, resulting in a net total of $15.2 million. RM&D has a variety of different tools that they use to diagnose and analyze a CAA. The problem that is currently being experienced is that there are so many tools it is becoming cumbersome to not only use but also to maintain. Each RM&D employee follows his or her own individual process as far as which tools to use to investigate and analyze a trip. The problem occurs when a tool does not function correctly and they have to resort to alternatives. This searching and opening of different tool programs to find one that will produce the desired information is an enormous driver of variability and wasted time. If all of the tools were consolidated into one program, then the employee would no longer have an individualized process, but rather have one set place to go in order to find all needed information. Not only would this standardize the process, but also IT would only have one program to update and maintain instead of the numerous in the current state. We predict that if the change was made to consolidate all tools into one program, it would result in an average time of about 33 minutes, increase the percentage of time under 30 minutes to around 57%, and increase the average number of saves per year to approximately 123, resulting in a save amount of $18.4 million. In comparison to the current state, we predict that if all recommendations are followed, RM&D will reduce their average processing time from 73 minutes to 33, increase the percentage of time under 30 minutes from 0.74% to around 57%, increase the number of saves generated from about 2 per year to approximately 123, and increase the amount generated from $236,550 to $18.4 million. This was not the only task we were charged with, though. We also had to categorize historical trips so RM&D could refer back to specific units in order to determine common trips per unit, trend patterns of failures, and have a detailed report of CAAs per unit for the customer.
The team collects and stores the communication between the team and the customer on each individual breakdown. The initiative is to identify the most common cause of control action advisory, in other words, major turbine failure, so the team can understand why the most failures occur. This analysis will help the team to provide the customer with increased value by improving the equipment uptime and identify better preventative measures. Our team was presented with an Excel database extract that contains all communication and possible category list. Data analysis showed that only for 2015 there were over 1,500 rows that required attention. In addition, very specific technical expertise is required to identify the proper category. This amount of information and limited project time constrained us from performing the manual analysis. We approached the problem from the different angle. We decided to develop a Visual Basic code that would automatically populate the categories. After multiple discussions with the GE team, we noticed that certain words or combination of the words in the customer feedback field tells the team what category to assign. Therefore, the customer feedback notes could be analyzed to see if the combination of the words are present. This approach allowed us to analyze a big amount of data in seconds. At first, we were asked to analyze only 2015 data, but with the developed code, we are not limited to 2015, but also can look at the previous years to get a better picture. Based on not fully populated categorization map, the results are very satisfying and show that our approach works. We were able to categorize 815 CAAs. The pivot table on the left helps us to identify the most likely causes. This information is very powerful and should be used to drive the reduction of the CAA response time. In addition, our R&D team should communicate the findings to the equipment design teams. This will assure that GE stays competitive on the tough market and the customers get best possible products and services. So next time you turn on the lights or plug something into the wall, think of all hard-working people here at GE who makes it possible to light up the world. Thank you, and Giga!